Good morning to everyone once again. Today is the second day of myself teaching you the chapter of class 11 science chemistry structure of atom. It is chapter 2. Okay. Now, in my previous classes, in my last class which I conducted, I had introduced to you wave motion and its characteristics. Okay. The characteristics of wave motion, I had discussed 3 points. Wave motion is nothing but a disturbance produced in the medium by the repeated periodic motion of the particles of the medium. Number 2, there is a regular phase change between the various particles of the medium. Each particle starts vibrating a little more than the particle just ahead of it. Number 3, the velocity of the wave is different from the velocity with which the particles of the medium are vibrating. So this number 3 is a very important point to keep in mind. So moving further, today's class, wave parameters. Let us come and discuss about the wave parameters in today's class. The first wave parameter which you see on your screen is called wavelength. It is called wavelength. The first wave parameter is called wavelength. So wavelength, the symbol by which it is represented is lambda, and it is defined as the shortest distance between points where a wave pattern repeats itself. Okay, so if there is a wave pattern like this, okay, so either this way or this way, okay, so that becomes the wavelength over here. Okay, now wavelength, as you have seen, it is very small. It is generally measured in angstrom or nanometer or picometer or micrometer, depends upon its length. Now the next parameter, as you can see, it's called amplitude. Amplitude over here, amplitude, this is amplitude. Okay, so amplitude, it is the maximum distance an object moves from its equilibrium position, maximum distance. So this becomes the amplitude, this becomes the amplitude. Okay, amplitude. Now the next one is frequency, F. Frequency is the number of complete oscillations going by a point in 1 second. That means in a time of 1 second, what is the number of complete oscillation? If I take the oscillation 1, this is one oscillation this way. Okay, so number of oscillations taken or completed in 1 second becomes the frequency. So these are the 3 important wave parameters which will be coming across in this chapter again and again. Moving further to one more term which is called wave velocity. Look at the diagram over here. Okay, this is the undisturbed position of the string. They have tied a string between 2 fixed points. Okay, and the string is made to vibrate. So the particle is going up, it is coming down, going up, it's coming down like this, and the direction of propagation of the wave is shown over here with the arrow over here. Okay, strong particle. Okay, now wave velocity is the velocity with which the wave disturbance travels in a medium, and particle velocity is the one with which the particle moves about its mean position. So there are 2 things to keep in mind over here. One is wave velocity, another one is particle velocity. Now wave velocity is the velocity of transmission of wave, whereas particle velocity is the velocity of particle vibrations. The particles vibrate, up and down. Now that was about wave velocity and particle velocity. Okay, now as you have seen in the previous slide over there, okay, in the previous slides you have seen already over there regarding this velocity over here, the velocity of a wave is different from the velocity with which the particles of the medium are vibrating. That means it is not necessary that the wave velocity and the particle velocity are same. They are different. The wave velocity and the particle velocity are different. That must be kept in mind. Now moving at one more thing over here, which is called wave number. Wave number definition, the reciprocal of wavelength. Reciprocal of wavelength is called wave number, and its symbol is this one, V, small v, above that we put a dash. That is called the symbol of wave number. Now unit, angstrom or nanometer. Okay, 1 angstrom is 10 to the power of minus 10 meter. 1 nanometer is 10 to the power of minus 9 meter. Okay, so you can see, to calculate the wave number, you should know the wavelength. So it is possible to get the wave number. So these are some important parameters. Okay, so going to detail, the first one, amplitude of the wave over here. As you can see, the definition: the amplitude of a wave is referred to maximum amount of displacement. Maximum, if there is a wave, if there is a wave over here. Okay, so this maximum displacement becomes the amplitude A. It becomes the amplitude. Okay, I can proceed further like this also. Okay, now from its rest position, then this measurement goes from rest to the first crest. From rest to the first crest. Crest is over here. Okay, and then this is called the trough. Okay, so you can have a look at this diagram also. It will help you understand more properly what is amplitude. Amplitude is given over here. Crest is here. Crest is here. Okay, these are the troughs. Okay, now moving to the next slide. After completing the wave parameters, we have something for you: the electromagnetic spectrum. Have a very nice look at this diagram, the electromagnetic spectrum, on which you can see the spectrum has been explained on the basis of wavelength, frequency, okay, the color combination, and the different waves over there. Okay, so first one, it's radio, 10 to the power of 3 meters. Then we have microwave, 10 to the power of minus 2 meters. Corresponding for radio waves, frequency 10 to the power of 4 hertz cycles per second. Then micro is 10 to the power of 8. Infrared, the frequency is 10 to the power of 12. Infrared, the wavelength is 10 to the power of minus 5. Okay, so these are the corresponding. Then visible is 10 to the power of minus 6. Okay, then ultraviolet 10 to the power of minus 8 is 10 to the power of 15. So as you can see, when the wavelength is increasing, the frequency is decreasing. They are inversely proportional to each other. So if the wavelength is increasing, the frequency will decrease. Okay, so that is one relation you have to understand from this electromagnetic spectrum diagram. Okay, now moving further to one more chart which will help you understand the various color bands in visible spectrum. The spectrum which is visible to us over here, visible light, it falls over here. So it is expanded between 400 nanometer to around 750 or 800 nanometer. Okay, that comes under visible spectrum. So it is VIBGYOR, VIBGYOR, VIBGYOR. Okay, so now here, if you see in the color bands in visible spectrum, the gamma rays, beyond gamma rays, there is cosmic rays. Okay, its wavelength is given 0.0001 nanometer. Then X rays are there, ultraviolet rays are there. Then comes the visible light over here. So from this chart, it is very important for you all to keep an idea about the wavelength of the visible spectrum between 400 nanometer to around 700 nanometers. That you have to keep in mind and remember. Okay, now let us move further and do some numericals based on the formula. Frequency is equal to C or by lambda. Okay, over here. Now the question says here, calculate the frequency and wave number. Frequency and wave number means this one. Okay, wave number, the formula is 1 by lambda. Calculate the frequency and wave number of a radiation whose wavelength is 480 nanometer. Okay, now to calculate, we can calculate all the three quantities that are frequency, wavelength and wave number if any one of them is given. This can be done by using the formula. I've written the formula already over here. Frequency is small v is equal to c by lambda. So wave number is v dash is equal to 1 by lambda. Okay. Now the value of the wavelength is given 480 nanometer. This nanometer means 480 into 10 power minus 9 meter. So, and then speed of light, c is speed of light. For radiation, the speed of light is same as this, 3 into 10 power 8 meter per second. And then now we first calculate this v is equal to c by lambda. So value of c is here, lambda is here. So upon calculation we get 6.25, that is frequency into 10 power 14 hertz cycles per second. After that get the wave number is equal to 1 by lambda. So 1 by 4, 18 10 power of minus 9 becomes the wave number. We're getting a value of 2.083 in 10 power of 6 per meter. So this is a very simple, basic, very simple problem based on the formula to calculate the frequency and wave number of radiation whose wavelength is 480 nanometers. So I request you all to practice like this sums from a textbook also. Okay. Now moving to the next slide. Moving to the next slide over here. There is another question. Question number 2 we can talk about. What is the frequency of violet light? Violet light wavelength is given 400 nanometer. So if I say 400 nanometer, this 400 nanometer becomes 10 to the power of minus 9 meter. Okay, now you got the idea. So applying this formula, or frequency is equal to c by lambda. So we get the frequency c by lambda over here. So put the values over there. Okay, speed of light you can take 2.998 or 3 into 10 to the power of 8 meter per second. You can use any one of them. So upon putting the values, we're getting the frequency as 7.50 upon simplification. 7.50 10 to the power of 14 hertz. Okay, as the answer. Okay, now let us have a look at the another sum. I think this is clear. These are very simple, direct formula based numericals. Okay, then this is a good question which I got after quite a lot of searching. Okay, it's a very good problem. It was asked in one of the competitive examinations, IIT, okay, and medical examinations. A dental hygienist, a dentist, that guy is using X-ray, and X-rays have a wavelength, and what you call of 1.00 angstrom. To take a series of dental radiograph, dental X-ray, while the patient is lying down, the patient is listening to a radio station, is listening to enjoying radio, okay, music, and the radio station wavelength of the signals, radio waves, are 325 centimeter. It is given in centimeter, mind it, okay. And this fellow, the patient, looks out of the window at the blue sky. Okay, so the color of the blue sky, which is reaching his eyes, its wavelength is 473 nanometer. So you have to be careful. In centimeter, here it is nanometer. Now, the question is, what is the frequency in per second of the electromagnetic radiation from each source? One source is X-ray, one source is radio station, one is the blue sky. Assume that the radiation travels at the speed of light, 3 into 10 to the power of 8 meter per second. Now, to do this sum, the hint is given. We are given the wavelength, so we can use the equation V is equal to C by lambda. Okay. Now to find the frequencies, however, we must first convert the wavelength to meters because C has units of meter per second. So this lambda for the radio waves, it has to convert it into meters. Okay, so that must be done. Now first, for the X-rays, see, converting from angstrom to meters. Okay, got it. Then calculate the frequency. Okay, so for the X-rays, V is equal to C by lambda, speed of light. X is like this. Okay, similarly we can get the frequency for what you call this radio waves also. V is equal to C by lambda, so 3 into 10 to the power of 8 divided by lambda. For this one is 325 centimeter, has to be converted into meter. So how will I convert centimeter into meter? How will I convert? Tell me, boys. Is it divided by 100?
Sir, divided by 100.
Yes. So
Yes, sir.
325 must be divided by 100. So 10 to the power of 2 goes up. So if you simplify this, you will get the frequency of the radio waves. Similarly, to get the frequency of the light which is coming from the sky, blue color light, again we apply the formula V is equal to C by lambda. So over here, the speed of light is same, 3 into 10 to the power of 8 divided by lambda. For blue light it is 473 nanometers. So 473 into 10 to the power of minus 9. So take this up. So simplify this, you'll get the answer for the what you call frequency of the what you call the blue color of the sky, which is reaching the observer or the patient. So I want you all to get the answer. This is already done for you. So I want you all to get the answer for the frequency for what you call this radio waves, and your frequency for the blue color of the sky, which is reaching the eyes of the observer, that is the patient. Okay, so this one was a very good question which was asked in one of the competitive examinations. Okay, so better solve this. I'm leaving for you to solve this one and this one on your own. Okay, now moving
Sir,
to,
can you please wait for a while?
yes, you want to copy it?
Can you please wait a while so I can copy
Yeah,
it?
yeah, copy. No, this I'll be sending in the WhatsApp. No, but you can write down the
Okay, sir.
working. You can write down the working if you want to. Okay, this
Okay, sir.
working,
Thank you, sir.
this is
So I,
for, this is for
I
radio.
have
Okay,
finished.
this is for radio. Okay,
Yes, sir.
this
Thank you,
one
sir.
is for blue sky.
Yes, sir.
Okay, this is a very very good
Yes, sir.
question. Okay, rare question. You will not find this question anywhere.
Yes, sir.
Okay, now I think I'll move to the next slide. Next
So I
question.
have finished.
Okay, very good. Thank you. Now this is the type of question which is asked in the ISC. One of the spectral lines of cesium. Cesium. Okay, I hope you remember cesium. Hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. Group 1A. It has a wavelength of 456 nanometer. 456 into 10 to the power of minus 9 meter. Okay, that's the wavelength. Now they are telling us calculate the frequency of this line. So wavelength is given over here. What is the wavelength given? What is the wavelength given? 400 and 400 and how much?
56.
456 nanometer.
456.
Now this 456
456
nanometer means 456
nanometer.
into 10 to the power of minus 9 meter. Are you getting it? Now for
Yes,
this
sir.
you have to use the speed of light, that is c. The speed of light is 3 into 10 to the power of 8 meter per second. Okay, now we know the wavelength, we know the speed of light. So to get the frequency small v, you can apply the formula. The formula is v is equal to c by lambda. Yes or no? Yes or no? So putting the values of the speed
Yes,
of light,
sir.
3 into 10 to the power of 8 divided by lambda. Lambda becomes 456 into 10 to the power of minus 9. So if you simplify this by using a scientific calculator, then you should get roughly, this will go up, it becomes 10 to the power of 8 plus 9, 17. So 3 divided by 456, you'll get around answer 6.6 into 10 to the power of 14 cycles per second, or I can say hertz. That is the unit for frequency. Okay, so this is how you must be able to solve simple questions based on the formula v is equal to c by lambda to calculate the frequency or maybe the wavelength of the, if the frequency is given then you can calculate the wavelength. Okay, now moving further to our next question. Calculate the frequency and wave number. Now they are asking wave number of light, yellow light, and wavelength of yellow light is given 580 nanometer. Very easy. Okay, step 1. See, first calculate the frequency of yellow light. V is equal to c by lambda. C is value is given. Lambda is nanometers, so convert it into meter. Okay, because the speed of light is in meters per second. Okay, now if you simplify this further, you will get the answer for the frequency 5.17 into 10 power of 14 per second or hertz. Okay, this is per second or hertz. Now to calculate the wave number, we know the wavelength already, so wave number is equal to 1 by lambda. So 1 divided by 5.17, or the lambda is over here, 580 10 power minus 9 meter. Okay, you get answer 1.724 into 10 power of 6 per meter. You get the answer, convert the answer in, get it in meter, per meter. Okay, so these are the different types of sums which I have solved you in today's class with regard to use the formula v is equal to c by lambda. Okay, now let us move further, my dear boys, to the part of this chapter next part of this chapter, which is called Planck's quantum theory of radiation. This is the next subtopic of the chapter. Now before jumping over here, let us have a look at this. The wave theory could not explain the energy distribution in black body radiations and photoelectric effect. Therefore, Max Planck studied the energy emitted by hot bodies at different temperatures, which led to the quantum theory of radiation. Okay, so he studied the energy distribution of various bodies, like this by plotting a graph, by plotting a graph. So, by studying this the energy emitted by hot bodies at different temperatures. As the temperature is rising, and the bodies start to vibrate more and more. So, based on these assumptions and concepts, he studied the energy emitted by hot bodies at different temperatures related to the quantum theory of radiation, which is called Planck's quantum theory of radiation. Now, here under Planck's quantum theory of radiation, remember, energy is not emitted continuously but discontinuously in the form of small packets of energy known as quanta of energy. Quanta means see, quantum, singular plural. Okay, quanta, quantum. Okay, now here one important thing to remember is if you go to a shop to buy a pen, can you buy two and a half pens? No, you cannot buy two and a half pens, but you can buy three pens. You cannot buy five and a half pens. You have to buy six pens or five pens. So, in a similar way, here also, energy is emitted by hot bodies, not continuously, but discontinuously in packets. And those packets of energy which are emitted according to Planck's quantum theory, they are called quanta of energy. The second point is the energy of each quantum is directly proportional to frequency of radiation. So the energy of each quantum is directly proportional to what? Frequency of radiation. Okay, so where E stands for energy and this small v stands for the frequency. So this is the main concept behind Planck's quantum theory of radiation. Now, moving further, little bit about the history over here. The Planck's quantum hypothesis in the year 1900, by using this formula, okay, he worked out the value of his constant h, which is called Planck's constant, 6.626 in 10 power minus 34 joules second. You don't have to remember this, but get an idea that this number is called Planck's constant. Okay, 6.626 in 10 power minus 34 joules second. Now, the energy of any molecular vibration could be only some whole number multiple of hf. Okay, if we have n as 1 or 2 or 3, these are integral multiple whole numbers. Okay, so energy of any molecular vibration will be in packets, in multiple simple multiple whole numbers only. Okay, now based on this, the energy of quantum E is given by E is equal to hv. Okay, h nu hv. H is a Planck's constant and its value is given 6.63 or 6 to 10 power of 34 joule second. According to Planck's theory, emitted energy or absorbed energy is an integer multiple of hv. hv 1 hv, 2 hv, 3 hv, but we cannot have decimals. We cannot have 2.5 or 3.5 or 1.5 and never a fraction of hv. Now Planck could not explain why energy is quantized, but his theory was able to accurately describe the radiation emitted by a hot object. That is why it was accepted widely. Okay. Now this fellow got the Nobel Prize after around 18 years, 1918, after completing his work. Later on, after that, moving to the next slide, he came to a relation, Planck's relation, E is equal to hv or E is equal to hc by lambda, because we know this frequency is c by lambda. So substituting the value of frequency by c by lambda, we get the relation also. So you must know this relation, learn this relation. It is called Planck's relation. E stands for energy, h stands for the Planck's constant, 6.6 to 10 power of 34 joule second. This small v is the frequency, c is the speed of light, and lambda is the wavelength. Now, looking at the salient features of Planck's quantum theory of radiation alongside, point wise, number one, radiant energy is emitted or absorbed discontinuously. This is an important point to note. The energy which is given out or absorbed, it is discontinuous, and it is in the form of small packets, energy bundles or energy packets known as quanta or photons. That is the important point. Number two, each quantum of radiation is associated with a definite amount of energy depending upon the frequency of radiation. Okay. The energy E, capital E of a quantum is given by E is equal to hv, where V is the frequency of the emitted radiation and h is known as the constant, which is called Planck's constant, named after the person involved in this work. E is equal to hc by lambda, E is equal to hc. If it is E is equal to hc, hc by lambda, and we know wave number is equal to 1 by lambda, so we can write E is equal to hc wave number over here. Okay. Now, number 3, a body can emit or absorb energy only in an integral whole number multiple of quantum and not in fraction of a quantum. So remember, under Planck's quantum theory of radiation over here, energy which is given out, which is emitted or absorbed, is always in an integral whole number multiple of quantum. It is never a fraction. So that is one question which can be asked under true and false or under multiple objective choice questions. Okay, so now moving further to the next concept over here, which is called photoelectric effect. After the Planck's quantum theory of radiation, we have the photoelectric effect, where you will try and understand this effect. Now, photoelectric effect is the phenomenon of what? Emission of electrons from the surface of heavy metals when light or any other radiation of suitable frequency falls on the metal. So, light having suitable frequency, if it falls on the surface of a metal. So metals surfaces, they have electrons, free electrons on the surface. Okay. Now the emission of electrons depends on the frequency of light, and the number of emitted electron depends on the intensity of light. So two things are there. The emission of electron depends upon frequency, and the number of emitted electron depends upon the intensity of light, with what intensity the light is falling on the surface. So this you have to keep in line, in your mind. Okay. Now Einstein's photoelectric equation is given below. Hv is equal to hv naught plus, this is the work function. This is called work function. Work function, it is the energy with which the light rays are hitting the metal surface so that electrons are given out. Okay, that is the work function. Okay, so hv is equal to hv0 plus half mv square. Now this h is called Planck's constant. Capital V, small v over here, v velocity of emitted electron, capital V, and small v is frequency of incident light, and this v0 is threshold frequency. Okay, and m, this is the minimum energy, minimum frequency required to be possessed by the light rays to emit electrons, and m is the mass of the electron. So I request you all to remember this relation. So this relation can be what you call modified in this manner also. Half mv square, have a look at this. Half mv square can be written as h and make h common, so we get h v minus v0. Okay, so this equation is also known as what you call Einstein's photoelectric equation. It was after this only that Einstein was awarded the Nobel Prize of Physics in 1921 on what you call, for his significant contribution to the mathematical physics. Okay, and also he made a huge contribution to the study of this chapter in chemistry as well. So you can learn this equation. You can learn this equation by marking it as equation number 2. Okay, both are known as
So,
Einstein's, yes, photoelectric effect. Yes, what is the question?
So what is threshold frequency?
Yeah, threshold frequency, it is the minimum frequency which is supposed to be carried by the light particle after hitting the metal surface. The minimum frequency required to emit electrons from the surface. Minimum frequency. Are you getting it? Did you understand?
Yes, sir.
Threshold frequency is the minimum
Yes.
frequency which is supposed to be carried by the light particle, so that after hitting the metal surface, electrons start coming out. Are you getting it? Minimum frequency. Now we can increase the frequency. If you increase the frequency, then emission of electrons will be more intense. Okay. And number, again, for the number of electrons emitted, we need to understand about the intensity of light. Whether light is highly intense or more intense or poorly intense, all those things come into play after that. Okay. I think this part is clear. Photoelectric effect to all of you. Is it clear? Is it clear?
yes, sir.
Okay, very
Yes,
good.
sir.
Yes,
Now,
sir. Yes, sir.
as I have told you, this V0 is frequency, threshold frequency. This is work function. HV0 is called work function. It is called work function. It is the energy required to overcome the attractive forces on the electron in the metal. So remember that also. Work function, it is the energy required. It is the energy required to overcome the attractive forces of the metal on the electrons on the surface. Okay, so that has to be overcome, then only electrons will be emitted from the metal surface. Okay, now moving to another concept over here in this chapter, which is called dual nature of light. Light has a double role. Light plays a double role after the photoelectric effect and during the Planck's quantum theory of radiation. Now, light can be modeled over here as a stream of particles. Particles, okay? The particles of light are called photons. Light can also behave as a wave. So, this is one thing. Light is behaving as a wave, it is behaving as a particle also. The best explanation of light is that it is particle that travels in waves. So, that is the best line over here. So, dual nature of light can be explained, can be understood and remembered and memorized by this last sentence over here. The best explanation of light is that it is particles. Light is what? Particles that travel in waves. Light is a particle that travels in waves. Okay, so that's why light has a dual nature. That's why light has a dual nature. Now have a look at this problem over here. There is a green light whose wavelength is 525 nanometer. Determine the energy for the given light in joules. Okay, to find the frequency first, they have done is c is equal to lambda into v. So we know this is given the velocity of this one 3 into 10 power of 8. So this is v is equal to c by lambda. So value of c is 3 into 10 to the power of 8 divided by 525. It is given nanometer. We have to convert this into meter. Nanometer is 10 power minus 9. Okay, so upon simplification, the value of v is coming to 5.71 into 10 to the power of 14 per second or hertz. Okay, so that is how we get the frequency. Now, to get the energy, the formula is product of Planck's constant into v. Okay, so Planck's constant we know it is 6.626 in 10 power of minus 34. Okay, multiplied by v, whatever we obtain 5.71 into 10 power of 14. Okay, if you simplify this, we get the energy in joules. So the answer is coming, it's already solved over there. I'm writing it once more, 3.7 10 power of minus 19 joules per photon. Okay, that is how you're going to solve like this problem. Okay, so don't get terrorized. If you know this formula, things will work out easily. Okay, now this was the basic sum based on calculation of energy. Okay, for given particular light in joules. Now, moving to the next topic for today, which is called atomic spectra. The spectra of an atom. When atoms are excited by photons, they emit light of certain wavelengths which correspond to different colors. Light of different wavelengths correspond to different colors in the visible spectrum. The emitted light can be observed as a series of colored lines with dark spaces in between. This series of colored lines is called a line or atomic spectra. So you can see example is given over here. Diagram of atomic spectra. Okay, in the visible spectrum. Okay, continuous over here. They are what? Continuous. Okay, so this is called atomic spectra. Now, after atomic spectra, you have idea about spectrum in your class 10 in physics also. A spectrum may be regarded. It is regarded as a plot of intensities of the constituent parts of radiation emitted or absorbed by a substance against the wavelengths. That means why we are seeing different colors, because the light falling on different substances, they absorb they absorb a particular wavelength color, and the corresponding complementary color is seen by our eyes of the object or for the object. That is why we have to keep in mind that a spectrum is regarded as a plot of intensities of constituent parts of radiation emitted or absorbed by a substance against the wavelengths, frequencies or wave numbers. Okay, in the increasing or decreasing order. So that is something about the spectrum which we have read over here. Try to go through this several times to get a better idea on this. Now, moving further in our next slide, have a look at this diagram. White light is falling on a prism and it is dispersing into the 7 colors. Okay, R O Y G B I V. Same thing here also. Red, orange, yellow, green, blue, indigo, violet, and the corresponding wavelength and frequency is given. So please remember the upper limit over here for red light and the lower limit over here for violet light. Okay, in terms of frequency and wavelength. For red color, it is 760. It is it is what 760 into 760 to 647 nanometer, and but for violet it is 424 into 380 nanometer. Okay, so this is for the dispersion or the production of spectrum by passing white light through a glass prism. Okay, now uh, I want you all to what you call learn the chapter till here and revise it before I continue in my next class. I would like to stop my class here only. Okay, and just hang on because tomorrow's class will be a very very important class, because if I start the next topic then it will not be able to complete because I have less time, so I'll stop the class here only. Okay, just hang on, just hang on before I take the attendance, and then you can leave. Okay. Okay, I have taken the attendance. Now you may leave the class. Thank you so much. Have a nice day.